Hello everyone and welcome to chapter 14, Acid-Base Equilibria. This chapter is going to be kind of an interesting mix of mostly equilibrium stuff, but then a good bit of just normal acid-base stuff that isn't necessarily equilibrium focused, but is related to the equilibria. So we're going to start off here by just talking very generally about acids and bases and defining what makes an acid and what makes a base a base. So you should have in Gen Chem 1 at the very least briefly talked about acids and bases. In my Gen Chem 1 classes we talk very briefly about acids and bases and about acid-base neutralization reactions, where you have a strong base and a strong acid. They react with each other and they make some salt and water. So just very generally. If you did not have that or you don't remember that from Gen Chem 1, no worries. We are going to cover all that basic stuff in this chapter as well. So, like I said, we're going to start off here by defining what makes an acid and what makes a base. But it's a little bit more complicated than that, because depending on where you go, and depending on who you ask, you might get different definitions of acid and base. And over time, that definition has changed as well. One of the first definitions is what's called the Arrhenius definition, which I would assume is the same guy that came up with the Arrhenius equation. There can't be that many Arrheniuses in chemistry, but I haven't actually double-checked that to make sure it's the case. But the Arrhenius definition says that an acid is a substance that when dissolved in water increases the concentration of hydrogen ions, and a base is a substance that when dissolved in water increases the concentration of hydroxide ions. So there's kind of two main parts of these definitions. Number one, it tells you what the acid or base is producing, and it has to be in water. So it's making H plus if you're an acid, it's making OH minus if you're a base, and it's doing this in water. And it is specifically for water, and so this definition is relatively limited in its applications. Now it is still very broadly applicable, because most of the chemistry that people do is going to be, at least in terms of acid-base chemistry, is going to be in water. There's lots of other chemistry that's not in water, but acid-base tends to be in water. And so it's still very useful, but it is more limited than the definition we're going to see in just a second, which is the one we're going to use mostly. But before we get to that definition, I want to very briefly talk about what hydronium ion is. So back here it said that we had hydrogen ions produced in solution. Another name for this is hydronium ion. The reason why we call it this is because when the H+, the hydrogen ion, goes into the water, it actually doesn't exist as H+. It exists as H3O+, because that H+ is actually just a proton. That's all that is, because hydrogen is a single proton and a single electron. The vast majority of hydrogen does not have any neutrons. There are some. Deuterium is an example of that, but they are very rare. The vast majority is just a proton and an electron, and so H+ is just a proton. And that's just simply not stable enough to exist on its own, floating around in water. Instead, it's going to find the nearest water molecule and attach to it. So it's going to attach to one of the lone pairs on one of the oxygens, because that positive charge is attracted to the negatively charged electrons. Opposites attract. And so you're going to form H3O+. So throughout all the rest of this chapter, we are going to use H+ and H3O+ interchangeably. Just realize that when I say H+, I'm really referring to this. It's just a whole lot easier to say H plus than H3O plus. It's a lot faster and easier, easier to write and easier to say. And truthfully, H3O plus is not the only thing that exists in the solution as well. You tend to form these nice little complexes with the hydronium ion, where other water molecules come around and don't really technically bond to it. It's not technically a molecule, that's why I call it a complex, but they are associated with it, and so they kind of act like a molecule, kind of. But the main point here is that anytime we talk about H+, we're actually referring to this, the hydronium ion. Alright, so on to that definition I teased you with. So this is the main definition that we are going to use in this chapter. It is called the Bronsted Lowry definition, and it is much simpler than the Arrhenius definition. According to Bronsted Lowry, an acid is a proton donor, and a base is a proton acceptor. So the Bronsted Lowry definition, first of all, is not attached to water. So you can have acid-base chemistry in terms of the Bronsted Lowry definition happening anywhere. And secondly, it's all about the protons. It's all about that H+. So the Bronsted Lowry definition is tracking where the H+ is going, and the acids are the things that are losing the H+, and the base is the thing that is accepting the H+, accepting the proton. So this is also sometimes called a proton transfer reaction, but usually it's just called an acid-base reaction. But if you want to get more specific as to the kind of acid-base reaction that's happening, you can call it a proton transfer reaction. And so as you can see in this reaction here, we have hydrochloric acid, and it is reacting with water, which is acting as a base. And so this H+ is donated by the acid to the base, which accepts it to become H3O+. Okay, so the key here is that Bronsted Lowry acids have to have a removable acidic proton, and acidic here just means that it's removable, that it's easy to take off of the molecule, because there are lots and lots of molecules, like this one, for example. So this is methane. Methane has 4 different hydrogens that, technically speaking, could be removed and go into a solution to form H+. That is technically possible for it to happen. But they are not easily removed. That carbon is holding on to those hydrogens really tightly. They are not easily removed, and so this is not acidic at all. So just having hydrogens does not make you acidic. Having a hydrogen that is relatively easy to remove is what makes you acidic. And then a Bronsted Lowry base has to have a pair of non-bonding electrons, which is to say a Bronsted Lowry base has to have somewhere for the H+ to go. So again, if you have methane, the methane here has no place for another hydrogen. There's no lone pairs. You're not going to have a hydrogen attaching to another hydrogen. There's really no place for it to go, and so this is not basic either. It's neither acidic or basic. So the acid has to have a hydrogen that's easy to remove, and the base has to have a lone pair for the hydrogen to go to, or for the proton to go to. Sometimes we will find some molecules that actually work in either direction. Things that can be either acid or base, just depending on what happens in the chemical reaction. And we are going to talk about that next time, and talk about how certain molecules can react in one way in one situation, and then react in another way in a different situation, just depending on what they're being paired with. So we'll talk about that, like I said, in the next video. And by the way, just kind of as a tease once again, at the very end, well, not quite the very end, but closer to the end of this chapter, we will actually talk about a third definition of acids and bases that's known as a Lewis acid and base. And we're just going to very briefly touch on that later on in this chapter. So you can look forward to that. I'll see you in the next video.